A single point of failure can dismantle the most complex engineering architecture on Earth. In 1942, the Imperial Japanese Navy aircraft carrier Akagi represented the absolute apex of naval aviation strike power. She was an 855-foot floating airfield designed to project overwhelming force across the vast expanse of the Pacific. But the fundamental physics of any aircraft carrier make it an inherently fragile platform. A carrier is essentially a high-speed industrial warehouse packed with thin-skinned aircraft, volatile high-octane aviation fuel, and exposed high explosives. This massive concentration of kinetic energy requires absolute control to remain safe. When that control is violently stripped away, the resulting chain reaction is mathematically unstoppable. Akagi was struck by a decisive direct hit from an American dive bomber, the point of failure. Accounts vary on the wider pattern of hits and near misses during the attack, but this 1,000-pound weapon punched through the flight deck near the middle elevator and detonated inside the upper hangar, triggering a chain reaction. The hit didn't break Akagi's backbone. Her keel and primary watertight bulkheads remained intact, but it punched into the one volume that could kill the ship from the inside. At the precise moment of impact, that enclosed volume was densely packed with aircraft being armed and fueled for a massive counterstrike. What followed wasn't luck or mystery. It was the hangar's geometry doing its work. When the American bomb detonated, it created a localized overpressure wave and a massive thermal spike. This initial thermal event instantly compromised the delicate structural integrity of the surrounding Japanese aircraft. Aviation fuel lines ruptured and spilled highly flammable liquid across the steel deck. Torpedoes and high-explosive aerial bombs staged loosely in the hangar were immediately exposed to direct flame and extreme temperatures. Heavy naval ordnance does not require a direct mechanical trigger to detonate if the ambient heat exceeds its critical thermal threshold. Within minutes, the first blaze had outrun every human hand on board. Secondary blasts ripped through the enclosed hangar in a devastating rhythm. Each subsequent detonation ruptured more fuel cells and scattered burning debris across adjacent parked aircraft. The heavily enclosed nature of the hangar deck concentrated the violent blast waves and trapped the expanding thermal mass. Fire feeds on oxygen, and the vast, open, continuous bays of the carrier provided an uninterrupted draft to accelerate the raging combustion. Damage control crews faced an impossible physics problem. The extreme intensity of the localized heat warped the steel bulkheads, melted the primary fire mains, and severed the vital communication circuits necessary to coordinate a ship-wide response. Water suppression systems were either completely offline or geometrically inadequate to smother a fully involved aviation fuel fire spreading across multiple decks. The engineering teams fought desperately to isolate the inferno, but the secondary ordnance detonations repeatedly breached their physical containment lines. Heavy steel decks warped and buckled under the sustained thermal load. Toxic smoke and superheated expanding gases forced the immediate abandonment of critical engineering spaces situated directly below the hangar deck. The structural integrity of the upper ship began to rapidly fail as the internal fire systematically gutted the central volume of the vessel. By the following day, the mighty warship was dead in the water, still burning from stem to stern. The fire had gutted the tactical heart of the ship, and there was no realistic way to tow an 855-foot inferno across thousands of miles of ocean while the battle raged overhead. Keeping her afloat under continued air threat would only spend more lives. On June 5, 1942, Admiral Isoroku Yamamoto ordered Akagi to be scuttled. Japanese destroyers Arashi, Hagakaze, Maikaze, and Nowaki closed the distance and fired torpedoes into the crippled carrier, flooding the engineering spaces. The ship rolled and quietly slipped beneath the surface of the Pacific. It vanished into a boundary of extreme depth that would deny any human reach. No human eye would see the wreck again for nearly 8 decades. Sonar would locate it in 2019, but the first close visual survey would not come until 2023. Sonar can reach where light dies, sketching an acoustic shadow from shape and dimensions, but at nearly 18,000 feet, it still stops short of absolute proof. Identity is confirmed by fine details, and fine details demand clean camera feeds. Getting that lens down there means first defeating the environment. The fundamental constraint governing any deep water survey is hydrostatic crush force. For every 33 feet a robotic vehicle descends, the ocean adds about 1 atmosphere of pressure, roughly 14.7 pounds per square inch, on top of what is already there at the surface. At nearly 18,000 feet, the overlying water column exerts crushing force against every exposed void. At that depth, the ocean is always trying to erase void space, to crush, compress, and invade anything that isn't solid. Every critical circuit has to live inside thick titanium pressure spheres or specialized oil-compensated housings. Even the buoyant syntactic foam slowly yields under load, quietly stealing maneuvering margin from the vehicle, and microscopic imperfections in rubber seals stop being minor and become fatal. A high-pressure leak forced past an electrical junction can cut like a jet, short power distribution, and sever the command link to the surface. In 2019, Akagi was located during a mapping survey of the Battle of Midway site conducted by Vulcan Inc. in partnership with the U.S. Navy History and Heritage Command. An autonomous sonar survey painted a massive return that matched the carrier's known dimensions and overall form. The sonar data was compelling, but it still left room for doubt without imagery. The expedition planned to follow up with a deep-rated ROV for visual confirmation, but the campaign was hit by hard reality. After a dive on Kaga, the ROV suffered damage beyond on-site repair. Without a functioning vehicle rated for that depth, the team had coordinates and an acoustic outline, but no eyes on the steel. Compounding this severe environmental hostility is a legal and ethical barrier that dictates the rules of engagement. The wreck lies within Papahanaumokuakea Marine National Monument, a heavily protected area where activities that remove, move, disturb, or damage resources are prohibited without a valid permit, with narrow exceptions for emergencies and law enforcement. And beyond the regulations, the site is a maritime heritage grave. That means no grabbing, no dragging, no test contact, and no clearing growth or taking artifacts just to settle identity. The survey teams were trapped between two absolute walls of denial. The physical wall of hydrostatic pressure destroyed their only means of looking at the ship safely. Simultaneously, the legal wall of the marine monument made any blind physical interaction a severe violation of international heritage law. If an exploration vehicle suffered a pressure casualty and crashed onto the fragile wreck, it would constitute a major breach of the non-disturbance protocols. The margin for error for any future exploration was exactly zero. The target remained isolated in the dark, protected by extreme depth and ironclad law. Bypassing this lethal physical barrier would require a completely new approach to deep ocean robotic navigation. In 2023, a specialized ocean exploration vessel arrived above the target coordinates with exactly one operational objective. The engineering team had to execute a 14-hour continuous deep water dive without triggering a single catastrophic failure in their remotely operated vehicle. The physical environment remained just as lethal as it had been 4 years prior. The hydrostatic crush force at this extreme depth dictated that every second the vehicle spent on the bottom exponentially increased the risk of a high-pressure seal breach. The pilots aboard the surface ship had to fly the massive robotic platform through the pitch-black water column using only acoustic positioning and isolated pools of artificial LED light. They were navigating a hostile threat matrix where the sheer weight of the ocean constantly tested the structural limits of their syntactic foam and titanium components. But the sheer operational complexity of reaching the seabed was instantly dwarfed by the mandate to identify the target without causing any physical disturbance. A traditional marine archaeological dive relies on scientists being physically present to brush away silt and analyze the debris field. At these extreme depths, that biological presence is fundamentally impossible. To bridge this physical gap, the expedition engineered a real-time expert network. This is the core mechanism of telepresence archaeology. High-bandwidth satellite uplinks streamed high-definition, encoded video feeds from the abyssal plane to the surface vessel. The shipboard systems then relayed those streams onward to shoreside command centers scattered across the globe. This continuous digital tether allowed remote experts to ride the dive in near real time, but not in zero time. Depending on the link and the viewer's access point, the delay could be as low as 1.5 to 2.0 seconds for the science team, with longer delays common for public distribution. If a particular steel plate or weapons tub drifted into the extreme edge of the camera frame, the remote network could immediately instruct the pilot to halt forward momentum and adjust the external lighting arrays. The ocean pilots executed the complex multi-axis thruster inputs, while the global network processed the historical visual data in real time. For 14 hours, telemetry, piloting, and remote eyes had to stay in lockstep without a single break. The remotely operated vehicle crept slowly along the abyssal plain until a massive steel shadow finally materialized in the forward floodlights. The expedition successfully achieved the very first visual confirmation of the target. As the camera swept across the towering hull, the global network instantly began matching the degraded structural contours against physical archival blueprints. Every heavily corroded bulkhead and collapsed deck stringer was cross-referenced by experts who had spent decades studying the exact architectural layout of the vessel. They systematically directed the cameras to scan specific operational zones where distinctive armament should logically reside, because the robotic system acted entirely as a remote optical extension of the global team. They never needed to physically touch the legally protected wargrave. The automated station-keeping software governed the hydraulic thrusters to prevent any sudden wash from stirring up the fine, deep-bottom sediment. A single cloud of disturbed silt could easily blind the high-definition lenses and ruin the visual pass. The expedition successfully projected human analytical power to the absolute bottom of the Pacific Ocean without once violating the rigid legal boundary of the marine monument. They proved the identity of the lost carrier exactly where the initial acoustic data had predicted. But simply finding the hull was only the first step in diagnosing the catastrophic internal trauma. A massive 855-foot steel structure resting upright on its keel presents an immediate geometric hazard to any robotic vehicle attempting to map its perimeter. When the expedition finally illuminated the primary target, they found the colossal warship upright, settled into the abyssal plain and partly embedded in seafloor sediment. This upright orientation is incredibly rare for a heavily armored top-heavy vessel, and it created a towering vertical cliff face of degrading steel. The remotely operated vehicle had to navigate this sheer metallic wall while managing a long, flexible umbilical tether that connected it to the surface. A single miscalculation in thrust could drag the tether across a jagged edge of shattered armor and instantly sever the primary power supply. The pilots were forced into a delicate mathematical dance, maintaining a strict physical standoff distance to guarantee the safety of the vehicle while pushing close enough to achieve total optical clarity. As the cameras slowly swept along the lower decks, diagnostic features emerged from the deep ocean gloom. Not a single magic talisman, but a pattern that locked into place. Overall dimensions, the torn sections of flight deck that opened sightlines into hangar volumes, and the arrangement of surviving gun positions and mounts all aligned with what historians expected of Akagi. The imagery captured recognizable detail, including twin anti-aircraft mounts beneath the flight deck that could be cross-referenced against wartime plans and photographs. Together, those converging markers pushed the identification past conjecture and into confirmation. But visually confirming a few prominent exterior weapons was not sufficient to build a comprehensive forensic model of the entire disaster. The scientific mandate required mapping the complete structural failure of the ship without violating the absolute prohibition against touching the hull. To bridge this operational gap, the engineering team relied entirely on the complex process of non-invasive photogrammetry. This optical mapping technique allows scientists to construct a highly accurate three-dimensional digital twin of the wreckage without ever making physical contact with the degrading steel. The remotely operated vehicle executes a series of highly structured geometric flight paths along the entire length of the hull. During these precise grid patterns, the optical payload captures thousands of overlapping, high-resolution images, enough to let software reconstruct geometry from subtle shifts between frames. These individual overlaps are then stitched into a three-dimensional model through photogrammetry, turning raw pixels into scale and structure. The result can yield highly accurate measurements of deformation and damage, often down to the scale of centimeters, derived entirely from passive optical data without touching the steel. Through the baseline guidance of telepresence archaeology, the remote team ensured every necessary visual angle was captured during the flight passes. They systematically built a flawless digital replica of the vessel directly in the computer memory. However, this purely visual approach inherently establishes a rigid proof ceiling. Non-invasive photogrammetry is strictly limited by the physical line of sight. The camera lenses cannot penetrate heavy layers of biological marine growth that obscure original paint lines or small builder plates. More importantly, the lenses cannot see through the deeply collapsed folds of heavy steel where the upper superstructure has catastrophically pancaked downward. Because the legal and ethical non-disturbance protocols are absolute, the robotic vehicle is strictly forbidden from moving a single piece of fallen debris to reveal what lies beneath. If a critical piece of forensic evidence is buried under a collapsed bulkhead, it will permanently remain undocumented. The external visual passes successfully documented the intact lower hull and the initial scuttling damage, but the upper decks presented a chaotic labyrinth of twisted metal. To understand the final moments before sinking, the cameras had to trace the path of the explosion from the inside out. An external aerial bomb strike often drives structure downward and inward, but the uppermost surviving levels of this wreck showed complex deformation that did not read like a single clean crater. In places, sections of deck plating appeared displaced, peeled back, or twisted into angles that hinted at violent forces acting from within, consistent with the historical reality of intense fires and a chain of explosions. But the wreck also carries the stamp of scuttling and the blunt physics of seafloor impact. From imagery alone, investigators can map the geometry of the damage and model plausible pathways for blast and collapse. Yet the exact sequence remains an inference built from patterns, not a laboratory certainty. The remote vehicle hovered over this chaotic labyrinth of upward-pointing steel and successfully applied optical mapping to measure the precise geometric angles of the bent deck plates. By meticulously recording the exact trajectory of the inverted structural beams, the scientific team could mathematically trace the blast pressure back to its exact point of origin within the heavily gutted hangar space. This pure data capture rendered any physical intrusion into the shattered hull completely unnecessary. The rule never changed: no physical contact, not once. In many traditional shallow water marine investigations, there is a strong institutional temptation to recover a twisted artifact or a piece of primary shrapnel to physically analyze the blast metallurgy in a dry laboratory. But extracting a heavy steel plate from the upper deck would require destructive industrial cutting tools, heavy lifting rigging, and prolonged mechanical interference with the wreck. The entire seabed surrounding the sunken carrier is officially designated as a strictly protected war grave. Absolute jurisdictional denial legally governs every single square inch of the surrounding debris field. The site stands as a permanent international heritage monument, and sovereign immunity protocols strictly dictate that the vessel remains eternally untouched by human hands. Any physical salvage attempt, no matter how scientifically well-intentioned or historically valuable, would fundamentally violate the sanctity of this final resting place. Furthermore, the sheer forensic clarity of the deep water optical data entirely eliminated any practical or academic justification for breaching this absolute legal boundary. The upward peeled flight deck stood as the ultimate physical proof of the internal thermal destruction. The preservation of this blast signature meant the forensic objectives were met without moving a single piece of steel. A traditional marine salvage operation defined success by the tonnage of steel lifted from the seafloor. But for this target, the victory was leaving the wreck exactly where it fell. In 2023, the expedition proved that zero physical intervention could still deliver a complete forensic record. They brought back an immense cache of imagery, then processed those passes into a three-dimensional model that captured the ship's geometry and damage without touching a single plate. That digital record closed the last remaining argument for breaching the monument's boundary. Identity was secured by optics, not by extraction. This pristine digital capture establishes a permanent baseline for all future monitoring of the site. The immense steel structure is actively degrading, consumed slowly by continuous microbiological corrosion and the relentless chemical action of the deep ocean environment. Heavy deck plates that initially survived the catastrophic hangar pressure wave will eventually succumb to this natural, invisible decay. The digital twin created by the real-time expert network preserves the exact geometric state of the vessel at this specific moment in time. Future generations of scientists can mathematically compare new optical passes against this primary baseline to measure the precise rate of structural collapse without ever touching the hull. The sheer remoteness of the location enforces an uncompromising isolation. The vessel lies protected as a sovereign war grave, and that legal shield is as real as the pressure above it. It ensures no commercial grab and no unauthorized robotic claw will ever disturb what remains inside the bulkheads. What was once an active mystery is now a monitored, untouchable site. And that is why the archive matters. The establishment of this digital archive fundamentally shifts the entire paradigm of deep water exploration. Instead of physically hoarding twisted metal artifacts in a dry museum, the global scientific community now shares a perfectly accurate virtual replica. This methodology protects the physical integrity of the protected monument while simultaneously democratizing the historical data. The immense volume of high-definition imagery generated by the robotic flight passes provides an inexhaustible resource for future naval engineers to study the ultimate limits of structural survival. They can continuously analyze the digital stress fractures and the shear points along the inverted flight deck without launching another multi-million-dollar physical expedition. Every coordinate recorded during the operation is tightly controlled by the governing heritage authorities. Access is managed through permitting, compliance, and enforcement, and the staggering cost of reaching nearly 18,000 feet already acts as a powerful deterrent. The site is protected not by science fiction surveillance myths, but by law, oversight, and the simple fact that the deep ocean is brutally hard to reach. That layered control helps ensure the non-disturbance protocols remain in force long after the exploration ships have returned to port. The operation proved that human ingenuity can bypass the most hostile environments on the planet through pure technological projection. It verified that a target can be successfully mapped, identified, and analyzed with zero physical footprint. The deep ocean effectively acts as a perfect, silent custodian for the shattered vessel. The heavy casemate guns and the warped armor plating will slowly dissolve into the abyssal plain over the coming centuries. But the digital legacy constructed by the operation will survive indefinitely. It remains frozen in the extreme depths of the Pacific, a permanent, untouched monument to a cascade of fire and steel.